Students, welcome back to section 5.5 of chemistry. Today we're going to talk about how do we visualize and work with the quantum mechanical model. Okay, so we want to be able to understand, connecting some things to your world there, what type of energy, this rock here that's listed in this picture here, would have less energy than before, but the position would be more stable. So when we talk about chemistry and chemical properties, again, this is where Rutherford model fell off. What are the chemical properties that this rock right here is going to? It has a lot of potential energy right now, but it's not very stable. When it falls and it settles onto the ground, hopefully no harming nothing in between, that it is less energy, but is more stable. So we're going to think about the relationship between stability and level of energy today as we talk about those. Okay, so we'll be talking about this throughout probably the next 3 or 4 chapters. When you think about energy levels, how much energy something has, a chemical or an atom has, versus its stability. So we're going to talk about electron configurations. Now, the issue with writing electron configurations, this is why we do this. When we imagine those sphere-shaped electron orbitals and the pear-shaped electron orbitals in the 3 different directions and the multi-Ds that we were talking about last time, that is very difficult to write on a piece of paper. And unless you're an incredible artist that is able to draw in 3 dimensions and without it getting confused, it's difficult to do that. So what chemists have come up with is what's called electron configurations, how to write on a piece of paper what orbital, S, P, or D, what energy level, and where do all those electrons live in all of these different orbitals. Okay, so we have these 3 rules we're going to talk about: the Aufbau principle, Pauli's exclusionary principle, and Hund's rule. And I'll tell you, we're going to talk about each one of these today. All right. So the first one's called the Aufbau principle. The Aufbau principle is very similar to that ladder we saw last time, is that electrons occupy the orbitals with the lowest energy first. Think of it as fruit on a tree. You're going to pick, if you're picking oranges or pears or apples off of a tree, or maybe off of a tomato plant, you're going to pick the ones that are easiest for you to reach. You're not going to climb up on the ladder just yet. You're going to pick the apples or the pears or oranges from your tree that are easiest to get to. Likewise, electrons fill lower energy levels or occupy lower energy orbitals first, and then they move upward. So in our little example here, in our little chart here, they're going to be in the 1s orbital and move their way up to the 2nd energy level and fill all of that energy level, move up to the 3rd and fill all of that energy level, move up to the 4th and fill that energy level. So just what you need to know from the Aufbau principle for now, even if you don't comprehend all of this, you will later on, is that electrons will fill the lowest energy, 1, then 2, then 3, all the different energy levels. You can still think those as the rings in the Bohr model, but now these are called orbitals. Okay, these energy levels are called orbitals. Okay, the Pauli exclusionary principle is that electrons will spin in opposite directions, and we have a way to note that. So if you'll have 2 electrons in each orbital, and they'll spin in opposite directions. So one will spin this way, and the other will spin that way. All right. So this understanding that they're going to spin in opposite directions, that's called the Pauli exclusionary principle. So they remain in pairs and they spin in opposite directions. The third principle, or the third rule, is that the electrons occupy orbitals in the same energy in the way that makes the number of electrons spin direction as large as possible. That'll come clear to you in a moment here, okay? So we're going to apply all of this to filling out this diagram here. So hydrogen, get out your periodic tables, pause the video if you need to go get your periodic table. You're going to need it. Now, if you look at hydrogen here, hydrogen on the periodic table has an atomic number of 1, which means it has 1 proton, and because it's neutral, it means it has 1 electron. So we'll be dealing with that 1 electron. So it is good that a 1 electron is going to fill its first energy level, which is the 1s orbital. The first energy level is the 1s orbital, the first energy, and then the first orbital in that energy level is the s orbital. So we denote that by an up arrow, meaning that that's 1 electron. And the electron configuration, how we would write that on a piece of paper, would be 1s1. And what that means is that it's in the first energy level in the s orbital, and that little exponent there stands for the number of electrons, 1 electron. Now remember, each one of these orbitals can only holds 2 electrons. Okay, so the most you'll ever see is 1s1 or 1s2. There'll never be a 1s3 or a 2s2, 2s3 or something like that. Okay, let's move on to helium. If you look on the very right hand side top corner of your periodic table, you will see that helium has 2 protons because it has an atomic number of 2, which means it has 2 electrons because it is neutral. So based on that, we fill the first energy level, and we have them going in opposite spin directions. Remember, in the orbital, one spins up, one spins down in our minds. That's how we think of it. So you would denote that as an arrow up and an arrow down. It fills the 1s orbital. So the electron configuration is 1s2. It says that the electrons are in the first energy level in s orbital, and there are 2 electrons there. That's what that stands for. Now let's continue on our path here. Lithium is element number 3. Atomic number 3, which means it has 3 protons. Because it's neutral, it has 3 electrons. So we fill based on the Aufbau principle, we fill our lowest energy level first with opposite spins. That's a Pauli exclusionary principle. And then we continue until we run out of electrons. So since lithium has 3, we move on to the next energy level in orbital, which is the 2s. So we have 1s, 2 that's filled, and then we have 2s, 1. So the electron configuration is 1s, 2, 2s, 1. So those are the electron configurations for the first 3. Let's jump down to another one here. Let's jump down to nitrogen. Nitrogen is element number 7 on our periodic table. And you'll see that it has 7 electrons then. So we fill our first energy level and first orbital, 1s2, and then we fill in our second s, 2s2, and then here's where the Hund principle comes in. So filling from least to greatest is the Aufbau. The opposite spin pair of 2 is the Pauli exclusionary principle, and then here's where Hund comes in. You fill the p orbitals, first time we're dealing with p, we fill the p orbitals in the same direction before we come back. So each one of these p's, you got one in the x, one in the y, and one in the z. So this electron configuration in the p orbital, so you have a total of 3 electrons in this p orbital. This just tells us what axes these are on right here, okay? X, Y, and Z. So the electron configuration is 1s2, get 2 in there, 2s2, 2s2, 2p3 because it's in 2, and you have 3 electrons in there. Okay, so let's get an example where you may have more to fill in that p orbitals. So we'll go down to fluorine. Fluorine is element number 9. It has 9 electrons. Pause if you need to look this up in your periodic table. So we have 1s2 that uses our first 2 electrons, 2s2 that uses our next 2. So we use a total of 4. So we have 5 left, 5 electrons left. So we put 1 up in each direction, and then we come back and put our downs. So this is the spin direction. This is our Hund rule. Our Aufbau we fill from least to greatest. The Pauli's exclusionary is 2 going in opposite directions when they're in pairs. And then the Hund rules, you fill in the same direction first, and then you come back in that orbital and go in the other direction. So the electron configuration is 1s2. There's our 1s2. 2s2, there's our 2s2, and 2p5 because there's 5 electrons in here. All right, so that is how we would do what's called an orbital filling diagram along with the electron configuration. Okay, so phosphorus is an element that uses and matches and has atomic number 15. 15, 1, 5, 5, 5. Okay, so that means it has 15 electrons if it's neutral. So, what would be the electron configuration? I want you to pause the video for right now and come back and write down on a piece of paper what the electron configuration was. Now, there are two electrons in each orbital, so we would fill those out in a very similar pattern that we did. So we'd have 1s2, 2s2, 2p6. We fill the entire p orbital out. So far we've used 2. And in the second energy level, we have 8, total of 8. 2 plus 6 is 8. So we've used 2 plus 8 is 10. 10. So out of 15, we have 5 left. We go to the next energy level and orbital, 3s2. So we've used 2 more. So we have 3 left, 3p3. Okay, so if you add up all these electrons, 2, 4, 10, 12, 15, we've used up all 15 electrons. So based on the figure on page 133 of your book, which is this figure right here, this table could help you out as well. Okay, so in class we've talked about a shortcut that I've taught you about the sideways, doing it on the sideways slant, and we'll continue to work on those together. Okay. So there are some exceptions to the course in everything in science. There's going to be an exception, and there are some that will be exceptions to that rule that they'll jump to more stable, and we will talk about those in specifically. But think about copper here. Copper has an electron configuration that's an exception to the Aufbau principle. Remember, the Aufbau principle is from least energy level to a greater energy level. So we'll talk about those particularly when we talk about the d orbitals. We'll talk about those in our next class. So that's it for today. What I want you to understand the most is how to write out an electron configuration for any element on the periodic table. I'll talk to you soon. Bye-bye.